Okay, so good morning. I will try to record. I don't know if the quality of the video will be good or not, but we want to continue the topic of differential equations. So today I want to talk about a very specific differential equation which is important, but I don't want to emphasize why it's important. I want just to teach you how to solve it in general. Okay, so let us assume that this differential equation that I write on the board is important. You want to explore different ways of solving this, okay? And when we are back in the aula and then we have the equipment, probably we can delve into a little bit more why this differential equation is practically important. So this is a differential equation in which the function y is unknown and a is a real number. And of course, I will assume that this real number is a constant real number is not zero, because if it is zero, then what happens? Then I am looking for a function y whose derivative is f of x. So technically speaking, this means that I need to find the primitive function for y. Yes? So primitive for little f. So this is why it becomes more interesting if a is not equal to 0. Before continuing, I want to introduce a piece of notation which is not, I don't know, for some reason absent from Math 4, but it is better to know about that, and that is the integral sign, because in Math 4 they use just integral sign with lower limit a, upper limit b for giving you, for example, a number. But this piece of notation I want to introduce, it will be, of course it is not still in Math 5 book, but I want you to know about it because that's just a simple piece of notation, okay? So if I give you a function f and I ask you what a primitive function for this is, I show it with capital F, I say capital F is a primitive function for little f if the derivative of capital F is little f. And of course, if one primitive function is capital F, we learned that all primitive functions are just that f plus at most an additive constant to it, yes? Okay, so now I want to introduce this piece of notation. So I use the same integral sign to write integral of f of x dx. But what do I mean by this symbol? I mean f of x plus a constant c. That's it. So instead of saying, so in Math 4, I gave you a function f of x, for example, x squared, and I ask you to find all primitive functions f of x. So what is all primitive function? Is just x to the power of 3 divided by 3 plus a constant. Now in this language, in this symbol, I just ask you to calculate the integral of x squared dx. Okay? So what does it mean? It means the set of all primitive functions. So whenever you see this symbol without any number here, no number there, it means it is asking you to write all primitive functions for this x squared. And that's technically speaking the same problem. So what you need to answer in front of it is this. Yes? And then of course when later this is called indefinite integral, and then the one that we learned in Math 4 having limits is called definite integral, yes? But I mean, I can understand why they haven't introduced this symbol in Math 4, but it is common in any other books in math. I want you to know it, and I think it facilitates our job here, even though this is not officially introduced in Math 4, Math 5 either. Yes, is that understandable? Okay. So, I want to solve this, and I want to introduce a technique that mathematicians have introduced to solve this problem, and that is multiplying the left-hand side and the right-hand side by this e to the power of ax. So whatever a constant a is, you find this function e to the power of that a times x, and you multiply both sides by this expression, okay? I don't know if I could come up with this idea myself, but this idea in differential equation is very common, and that one is called an integrating factor. But let me try to ask yourself, why do you think this is useful? So let me multiply everything by that expression. Let us see what happens. If I multiply the left-hand side by this expression, it becomes e to the power of ax multiplied by y prime. This becomes plus a e to the power of ax y. And on the right-hand side, I will have e to the power of ax f of x. Okay, so usually this is not very common in mathematics because I am making my problem apparently more complicated because the form that I get is more involved than the one that I already had. Okay, so why do you think it's beneficial here? Do you see any pattern? On the left-hand side especially, because the right-hand side nothing to do, we don't know f. But the left-hand side, if you're observant enough, you see that's a pattern, yes?
A e to ax is the derivative of e ax, right?
Okay, but then what the pattern is, yes?
It's the multiplication rule.
Product rule, yes, exactly. Yeah, because then this is the right-hand side of a product rule, as we learned in Math 4. If I have two functions f, g multiplied, and I want to differentiate it, you differentiate the first one multiplied by the second one itself, plus the first one multiplied by the derivative of the second one. And if you compare the right-hand side of a product rule with this one, you immediately realize that this one is the right-hand side of of the derivative of a product. Which product is that? You need to write some product here so that when you expand it using that rule, it gives you this one. What is that?
To power ax times y.
Yes, e to power of ax times y. Yes. Let us double check. The derivative of the first one, let me write it here. The derivative of the first one, a goes down, the function repeats itself, multiplied by the second function itself, which is the second term here, plus the first one multiplied by the derivative of the second one, which is the first term here. So what I have done is right, yes? And then I have e to the power of ax f of x here. Okay, and then I am looking for this. This is still unknown. Why this is unknown? E to the power of ax is known to me, but still y is unknown. Y is what I'm looking for. If y is unknown, the whole combination is unknown. But I know something about this unknown. I know its derivative is this combination. So then if I ask you what this one is, what do you say? A primitive function of this combination, whatever it is. And using this symbol that I introduced, I would say that e to power of ax multiplied by y is equal to all primitive. So the answer to this could be any primitive function of this combination. And using that symbol, I would write integral e to the power of ax f of x dx. Instead of writing all primitive functions of this, I symbolize it by that. But as usual, I am looking for y, so I isolate my y, so I divide everything by e to the power of ax, or equivalently, I multiply everything by e to the power of minus ax. And so what happens, the right-hand side, the left-hand side becomes y alone, the right-hand side becomes e to the power of minus ax, integral of e to the power of ax, f of x, dx. And be careful, you're not allowed to flip this inside because it depends to x, so it's not a constant. Only multiplicative constants can be pulled out or flipped in. This is not a constant. That's what I can write. I have to stop there. Yes? Yes, okay, but you will be on YouTube if you pass here, no worries. Because there is no pause button there. Or you can just go a little bit there. Anyway. Okay, so is that understandable? But can I consider this the general solution of my differential equation? Or this is just a solution? Let us review. What was the general solution? The general solution has two properties, yes? First of all, it is a solution. Secondly, It contains, yes. Secondly, it contains as many free parameters as the order of your differential equation. So what is the order? Do you remember? Or completely forgotten? The order was the order of the highest derivative in the differential equation. So here, the order of this differential equation is 1. So when I say I have the general solution, what do I mean? I mean I have a solution, and that solution contains one single free parameter. But is there any single free parameter here? Yes?
Yeah, one.
Which one is that?
Or the C that we don't.
Yeah, we don't see. It's invisible. So some people say A, but I want you to understand A is not the free parameter. Because A is given to me from the beginning of the problem, whatever it is, 5, 7, whatever it is. It's a constant given to me. It's not a free parameter. The free parameter does not appear apparently, but I told you that in this symbol, it means that I write the capital F, meaning a primitive function of this but plus a constant C. So the constant C is hidden, is invisible in this formula. So that's completely correct. That's the general solution of the differential equation. And we can say this is the end of the story, but this method is not given in the book, and there is a reason to that. Okay. Okay, any questions so far? In principle, I can say whenever you see this problem, you can always solve it like this. You know what, if I want to compare it, if I give you a quadratic equation, whenever you see a quadratic equation, you use ABC formula to solve it. Yes, this is more or less the same thing. I haven't motivated you why this differential equation is important in the first place, but let us assume that this is important. This lesson, you want to learn how to solve this. And this is the solution. Okay? But the problem is that calculating a primitive function of this combination is not that easy usually. And that is because we have a product. So if you pass here, you will be in YouTube. There's no pause button. Yes? No words? Yeah. Okay. So let me, before giving you a lot of words, let me start with a very simple problem that we can solve. Okay. So if I give you y prime plus 5y equals to, let me make it simple, but at least non-trivial. So let me write 2. Okay. And then, of course, I forgot to mention that this method depends that this constant is 1. Okay, if this constant is not 1, what should I do? For example, let us say it is, let me put it here. Okay, so let me start with the 2 here. Okay, so yes? First I have to divide by 2. So in order that this method works, because of this pattern, emerges only if this is 1, so you have to make sure that this is first 1. By the way, can you guess the function? I just want you to see that this differential equation is probably the simplest possible function, but still, can you guess? It's not hard. If you think a little bit wiser, you should be able to guess the solution. I want a function whose that function multiplied by 5 plus 2 times its derivative, it becomes the constant number 2. Just give me the function.
A constant function.
No, not any constant function. It should be, because, for example, x equals to 7. Y equals to 7 is a constant function, but it doesn't work here, because the derivative of the constant is 0, and then 5 times it's 35, not 2. So you have to fine-tune that constant function. Yes? Yes, it is 2 over 5. So the constant function 2 over 5 is indeed a solution. Why? Because its derivative is 0. When I put these here, 2 times 0 plus 5 times 2 over 5 is 2. But this is not the general solution. It's a particular solution. But what is the general solution?
2e to the power of minus 2 over 5x, the indefinite integral of e to the power of...
Okay, so you're calculating. Okay, I'm just trying to guess. Okay, let us calculate. Okay, so the first thing that I want to do, you need to make sure that this number is 1. In my case, first of all, do you see that this is today's lesson? Yes, because this differential equation is comparable to that one. but I have to make it right first. Making it right means that I have to make sure that this one is 1 if I want to use this method that I described here. So I divide everything by 2 first. So what happens? It becomes y prime plus 5 over 2y, and the right hand side becomes 1. And then what is my integrating factor now? Integrating factor is for this differential equation is this one. Why this is called integrating factor? Because when you multiply this, the left hand side becomes the derivative of a function. And then you can integrate or find primitive function. Okay, so what should I do? This time I have to multiply by what? It's on the board. E to the power of ax. A is 5 over 2, so I multiply everything by that, yes? I multiply the left and the right by this factor as I described there. So this becomes e to the power of 5 over 2 y prime plus 5 over 2 e to the power of 5, sorry, y over 2x, 5 over 2x, y equals to e to the power of 5 over 2x. Are you with me? So I divided by 2, and then I use my memory to write the integrating factor, and multiply both sides by integrating factor. And you don't doubt, you can of course double check, but this left hand side always becomes the derivative of a product. Which product is that? E to the power of 5 over 2 times y prime, and on the right hand side I will have this. Yes? If you want, you can double check. So I don't know where I put it. Yes. So the derivative of the first one is this combination multiplied by the second one, which is this, plus the first one multiplied by the derivative of the second. So everything is on order. So now e to the power of 5 over 2x times y is equal to, what should I write? Integral means primitive function of this expression. Yes? But again, in the language of Math 4, I am asking you find all primitive functions of this function. So what is happening? So it becomes e to the power of 5 over 2x. Y is equal. So do you remember in the Math 4 exam? So 1 over k, but this is k, so 1 over k becomes 2/5, but the function repeats itself. And then plus a constant. Yes? But I am looking for y, so I have to divide everything by that expression. So this becomes 2 over 5 e to the power of 5 over 2x over e to the power of 5 over 2x, and then plus c divided by e to the power of 5 over 2x. So this one and that one are gone, and that's exactly what you could guess. So it's y equals to 2 over 5, but plus c e to the power, I bring it up. This is common that we write with negative powers in differential equations, but that's up to you. This is the general solution of this differential equation, and of course you see that you were able to guess one of them, but not all of them. That one is a particular solution which can be obtained from the general solution by assigning 0 to this constant value. Okay? But the set of all possible functions was not that easy to guess. So we are doing something, even if for this, if I have it for this very simple differential equation. Yes, is that right? Okay, I want to give some examples before going to teach you a different method. I want to motivate why, even though technically speaking this is a good method and it solves every problem of this type, why still we prefer to use a different method. Okay, but before reaching to that, let us try to give you some examples. Any questions so far? Okay, so now let me keep this. So I want to keep it on the board. So the integrating factor, so don't forget, this is always the integrating factor. Let me give you another differential equation, and let us see how it works. So I would write y prime plus, let me write 3y equals to 5, let me write here e to the power of 2x. Okay. So we want to find the general solution of this differential equation now. And of course, you can immediately compare the equation that I gave you with the standard one, and you see that this is exactly that differential equation. A is 3 and f of x is that one. Yes? So it will be on YouTube if you pass from here, okay?
Okay.
Okay. So I will follow the same method that I mentioned. What should I do? I have to multiply everything by that integrating factor. This is already 1, and this a is 3. So I have to multiply everything by e to power 3x. Yes? So it becomes e to power 3x y prime plus 3 e to power 3x y is equal to 5 e to power 3x. I intentionally write it like this. I want to see why. Yes, so I multiplied everything by that integrating factor, and this is always the case. You don't need even to think twice. It becomes e to power 3x times y totally prime. Yes? Yes? And the right-hand side, it's an exception, you know. These can be combined. Because in principle, if I ask you what is a primitive function of this, you remember there is no product rule for primitive functions. So you cannot say that, okay, I calculate the primitive function of this bit, I calculate the primitive function for this, then multiply them. Unfortunately, there is no product rule in a very simple term for primitive functions. But this is one of those exceptions, even though it is a product, but it can be combined into one single function. Okay, so here what can I write? I can write 5e to the power of 5x, because the bases are the same. I write the same base and I add the exponents, yes? And now everything is in order. So e to the power of 3x times y is the set of all primitive functions for that. So I can write it as integral of 5e to the power of 5x dx. And then my duty is just to calculate the set of all primitive functions for that. Yes? Okay, so what should I do now? This is a very simple, even math 3C problem. I want to find all primitive functions for that combination. So it becomes e to the power of 3xy is equal. So what's that? 5 is a multiplicative constant. A primitive function for e to the power of 5x, 1 over 5 goes down, and the function repeats itself, but I have to put a constant there as well. And then this 5 and that 5 are gone, so y becomes, I have to divide everything by e to power 3x. E to power 5x divided by e to power 3x, it becomes e to power 2x. And then c divided by e to the power of 3x, I write it with negative exponent. So that is your general solution to this differential equation. Yes? But now let us say that I change this differential equation. Any questions here? So we are learning how to solve that differential equation. And the method of integrating factor works for all cases. The problem is somewhere else. So, for example, let me write this function, this differential equation, and I make it even simpler than before. So y prime plus y equals to x. Can you guess the function that works here? So I just want you to know that even though differential equations are so simple, but might be guessing is not that simple, okay? So this differential equation apparently looks simpler than the previous one, and then you see that why I am facing a problem here, okay? So I want to follow the same rule. So what is my integrating factor here? So you see a is 1, f of x is x, so this in principle should be solved. I should be able to solve it using this method. So my integrating factor is e to the power of x itself, because a is 1 in this problem. I multiply everything by e to power x. So I multiplied my differential equation by that. And then as usual, this is always a product rule. Double check the derivative of the first one, which is this, multiplied by the second one itself plus the first one multiplied by the derivative of the second. That's correct. And this becomes x e to the power of x. And then, what should I do? I need to find x e to the power of x times y by writing the integral of x e x dx. Okay, so that is the problem here. It is not a hard integral, but for some reason it is not in your course. So if I want to continue, even though I know a primitive function for x is x squared over 2, I know a primitive function for e to the x is e to the x itself. But if you ask me what is a primitive function of a product, this is not correct to write this multiplied by that. So that one is not correct. Yes? You can check it. If I ask you to differentiate this, it becomes the derivative of the first one x multiplied by the second one e to the x, but plus the first one multiplied by the derivative of the second one. So you see that the derivative of this combination is not this one, it's this one plus something else. Okay? So it is not equal to this. So I cannot say that, okay, I find a primitive function of this, a primitive function for that, then I multiply them, it becomes a primitive function for the product. It doesn't work. And in Math 4, I also told you that there is no simple product rule for primitive functions. Okay, so this is the reason that the book doesn't talk about this method, which is the general method. The reason is that finding a primitive functions are not usually simple when you multiply them, and mainly the obstacle is that we do not have any formula for the primitive function of the product in general. But can you guess? Can you guess a function whose derivative is x e to the x? So my question is that, can you guess a function whose derivative this becomes that? Because if you can, then you are done. You write that function you guessed plus a constant, you divide everything by e to the x, y becomes isolated, and that will be your solution. Of course, I'm asking you too much probably, because this is a method called integration by parts. You will study that in university, but it's not too advanced. I mean, the first calculus course that you will take includes that method. Yeah, but can you guess now? Okay, let me help you a little bit. Let us take the derivative of this function. It's a little bit strange because I am looking for a function whose derivative is this. I am asking you to differentiate this. What happens then? It becomes the derivative of the first one, 1 multiplied by the second one, yes, plus the first one multiplied by the derivative of the second one. But the derivative of the second one is the function itself. Yes? Yes?
Is it x e to the x minus e to the x?
Yes. Yes. Why? Because here you can go a little bit further. Instead of e to the power of x, I write e to the power of x derivative. Don't try to see why I'm doing this. Just see that it works. Okay? So then it becomes x e to the power of x. Then I move this to the other side. It becomes x to the prime minus ex prime is equal to x ex. And then this prime here, a prime there, but I have difference between them. It's a Math 4 lesson to know that I can write x ex minus ex totally prime. Because if I ask you to differentiate this, you differentiate this bit, you differentiate this bit, you subtract them. That rule works. And then you have x e to the x. And now compare this with this one, you can read the question mark easily. The question mark is this function. Yes? So if you could somehow come up with that, then you are done. Why? Because you continue one more step. You say that this is e to the x times y is equal to, instead of that one, what do you write? You write this function that you found. which is x e to the x minus e to the x, but plus a constant. And then I want to isolate y, so I divide everything by e to the x. If I do that, so let me write it here. If I divide by e to the x, this is x, this is minus 1, this is c over e to the x, I bring it up, and this will be the general solution. At least, by this example, you see it still works. The only problem in front of you is that finding primitive functions of product are in general not simple. Okay? Any questions? So now, at least this example motivates you. Even if I have a very simple function like x on the right, I might face some problems. This problem will not rise if I have a constant number there, or if I have an exponential function there. Why is that? Because if I have a constant, when I multiply it by the multiplicative, by the integrating factor, it becomes a constant times e to some power, which I can solve. And if I have an exponential function like this, still I have a product, but the good news is that these two can be combined into one function. So, if you like, if that number is a constant, or that number is of this type, e to power something, first degree polynomial, then you can use this method. But let us try to see what is method presented by the book. The method presented by the book, which is of course also a very important technique in solving differential equations of different orders, not just first order, is the method of undetermined coefficients. Okay? So we want to describe that. So So this is my differential equation. I want to solve it, but using the method of undetermined coefficients. But let me give you the algorithm, and then I try to convince you why the algorithm works, and then let us see. Then I will tell you how to use the algorithm. So the algorithm tells you that what you need to do, you need to solve this equation with 0 on the right-hand side. Okay, this differential equation is called the homogeneous differential equation corresponding to this inhomogeneous differential equation. So if this is not 0, it's called inhomogeneous. If this is 0, we call it homogeneous differential equation. So let us solve that. Okay, so let me write like this. Solve y prime plus ay equals to z equals to 0, and find its general solution so I emphasize on the word general here, y sub h, h for homogeneous. So when in differential equation, when the right hand side is 0, we call it the homogeneous differential equation. So if you want to solve this inhomogeneous differential equation, this algorithm tells you that momentarily forget about the right hand side, replace it with 0, and solve the this homogeneous differential equation and find the general solution and call it h sub y sub h, h for homogeneous. Number 2, find, here by find I mean you are also allowed to guess. Find a particular solution I call it y sub p, p for particular, of y prime plus a y equals to f of x. Yeah, this seems a little bit strange, but you will understand it makes sense. Number 3, the general solution that you are looking for is claimed to be the general solution that you got for the homogeneous part plus the particular solution that you got here. If you add them up, it will give you the general solution of the original differential equation. So if I give you this differential equation, put 0 and solve, find the general solution. Find, here find is a little bit problematic. It means that either you can guess or whatever. Because sometimes guessing was easy. Do you remember? When I asked you to guess, you came up with the answer y equals to 5 over 2. Do you remember in that example? Which I don't remember exactly what was that. For example, if I ask you to guess a solution to this, you can immediately guess. Yes? What is that? A solution, not the general solution. The general solution is not that easy to guess, but a solution is easy. What is a solution here? Y equals to 1. Yes? So you see, guessing sometimes is easy. But the method of undetermined coefficient is a mixture of guesswork and analytic work. I will describe it how. Okay? So let us learn the algorithm. I give you this and I ask you to find the general solution. What you do first, you ignore the right-hand side, replace it with 0, and find the general solution of the easier problem, the homogeneous one, and call it y sub h. In any way, you find a particular solution, which is sometimes easier than finding the general solution. If you could do that, then this algorithm tells you that whatever you found in the first step, added to whatever you found in the second step, this becomes the general solution of the differential equation which was given to you in the beginning. So first of all, is the algorithm clear? But it is not clear why it works. The first thing I want to convince you is that might be it is not a good idea. Let me try to use it before convincing you it works. Okay? So let us take this one. Okay, so let us try to see what algorithm tells us.
Wait, sorry.
Yes.
What was it that we found?
What?
In the first step.
In the third step, nothing. You just add whatever you had there, and this becomes the general solution of differential you are looking for.
But wait, why is y of h also called the general solution?
No, this is general solution of the homogeneous one.
Right.
Yeah. So, in order to understand the algorithm, let us start solving this differential equation. If I ask you to solve this differential equation, you have the method of integrating factor already, and it is easy to establish it here. But let us use the algorithm. If I want to find the general solution of this one, the first step is not to solve this one, is to solve the homogeneous one. Yes? This can be done using integrating factor always. Yes? What is the integrating factor here? It's e to the power of x. So I multiply it by e to the power of x. So it becomes e to power x y prime plus e to power x y is equal. Because this is 0, it's good news. It remains 0. Nothing will change. Yes? So I'm just using the method that I described before the algorithm for this very simple one. I found the primitive integrating factor. I multiplied both by this. The right-hand side remains 0. The left-hand side, as usual, becomes a complete derivative. And the right-hand side is 0. Now my question is that I'm looking for this, so I need to find all primitive functions for 0. So what should I write? It becomes integral of 0 dx. But what is this?
C.
SC. Yes? Yes? And then what do I do? So y becomes c divided by e to power x, which becomes e to power minus x. So no worries. This method always works for the homogeneous one because the right-hand side remains always 0. And then this I equip it with an index h because this is not the one that I am looking for. this is the general solution for the homogeneous part. Step number 2. So step number 2, what should I do? Find. I haven't talked about how to find, but guessing here is okay. Can you just guess? Yes, we did. What was the guessing for this one? Not the general solution. I don't want to find all of them. Finding all of them might be a little bit cumbersome, but guessing one is not that hard. You guessed. What was that function? It was just 1. Yes, because if you put it back here, the derivative of 1 is 0 plus 1 is 1, so that's correct. So whatever you could guess that works, that is good for your purpose. You call it y sub p. And then number 3, you are done. The solution of that differential equation is yh plus yp. So y is equal to yh is that, yp is that, so it becomes ce to the power of minus x plus 1. That's it. So this is essentially what the algorithm is telling you. I haven't told you why it works, but I'm telling you by this simple example how to find it.
So this method is only useful if it's easy
To guess.
a single solution.
Yes, yes.
And that is generally
Not easy. Yeah. But at least you understand the algorithm. Yes?
Yeah.
Okay. I think you understood the algorithm. At least you understood that it might save you some time, because guessing this was not that hard, not that easy, but guessing it was fairly easy. So it's not completely useless algorithm. Yes? Okay. But before doing that, let us try to understand why the algorithm works in the first place, and then we go to a little bit harder questions, more interesting ones. Okay, so why this algorithm works? I need to clean this, okay? Is that okay? I want to ask your opinion. We want to convince ourselves that this algorithm works. Well, I have 2 duties to do, because look at the last one. I want my claim is that this combination in which yh is got from here, is got from here, and yp is get from here. So then this will work for that one. I need to convince myself this y is the general solution of the differential equation given in the beginning. I have 2 duties to do. What are they? If I want to show that this is the general solution of this differential equations, I have to investigate 2 things. 1, I'm just reviewing things. That's very simple. 1, yes?
You have as many parameters as.
Okay, that's the second one. The first one is that it works. Yes, I have to show that it works in this differential equation, meaning that if I replace y with this combination, it really becomes f of x. And then I have to convince myself that there is one and only one single free parameter there. Yes, because my differential equation is of the first order. Okay, so when you say y of h is the general solution of this, so I would say that yh is the general solution of what? Of this differential equation. From this sentence, I can conclude what? I can conclude that it fulfills the equation. Yes, it satisfies my equation. So what happens? It means yh prime plus ay sub h is indeed 0, and call it number 1. This, what you see on the board, is the summarized of that English sentence in mathematical way. And then I know that according to this part, yp is a particular solution of y prime plus ay equals to f of x. Okay, from this sentence, what can I conclude mathematically? Yp prime plus ayp is equal to what? F of x. Let me call it number 2. Okay, now my claim is that this combination is a solution of the original equation. So I have to convince myself that if I put it in the differential equation, it works. Okay, so I go to the left-hand side of that differential equation, replace every appearance of y with the claimed combination, and try to convince myself that this is working. Nice. If I succeed to show that this is indeed equal to f of x, which is the right-hand side, I am done. But that's also very simple, isn't it? Because the derivative of a sum can be written as the derivative of the first one plus the derivative of the second one. And I multiply this a in, and then I arrange them, I group these together, plus I group these together. Yes? And then, according to number 1, what can I write for this combination? 0. According to number 2, so number 1 and 2 are being used here. So instead of number 2, I can write f of x, but 0 plus f of x is f of x, and that is equal to the right-hand side. Yes, that's it. I mean, the algebra is extremely simple, but it's good to see it once. Yes? But why it is the general solution? This doesn't show it is the general solution. It shows that it works with this differential equation. But how can you argue that there is one single free parameter there in that combination? Why is that?
Because it's only one.
In YH. No, why there is. So I know that this works, but how do you know that there is one single free parameter in this differential equation?
Because in YH there's only one.
Yeah, because YH was what was the general solution. Based on definition of the general solution, it contains one free parameter. YP is a particular solution, no free parameters at all. And when I have this combination, what happens? Then I will have a one single free parameter. That's the proof why the algorithm works. Okay. By the way, what you need to know about the property that works this is important to understand. This is called a linear differential equation. Okay. So if I have a linear differential equation of this form, so I would say y prime. A linear differential equation is a differential equation in which the coefficients are at most functions of x. So for example, if I write, I don't know, sine x, y equals to whatever you like, you can write on the right-hand side. So a linear differential equation is a differential equation of this type. Okay? This is called a linear differential equation. Be careful. This coefficient is a function of x only. Because in general, I can write y equals to, I don't know, y prime plus, I can write here 3 over y plus 1, and then y equals to f of x. You see, this coefficient of y is not a function of x. It is a function of, I can write a mixture if you want to. So let me write a little bit easier. So let me write y prime plus x, y plus 1 times y is equal to f of x. This is not a linear one. Yes, because this is comparable to that, this is comparable, that's okay, but this one, which is the coefficient of y, does not depend only on x, as is demanded for a differential equation to be linear. It depends on both x and y. So this is non-linear. The theory of nonlinear differential equations is extremely hard. And then this is linear. Okay, let me talk a little bit about that, why a linear equation is simpler to solve, or at least to investigate. Because if I have two particular solutions of a linear differential equation, the sum is always another solution. Yes, that is the important thing. Okay. Okay, let me talk about that linearity a little bit later, because might be you get confused. Okay, I will talk about linearity a little bit later. So I will come back to this again. Okay. Now let us go back to the algorithm. Which part of this algorithm is problematic? The second. Because the first one is just nothing. If you have the first one done, the second one done, the last one is just adding them up. The first one is always easily possible, and it is in the formula sheet. So the general solution of this differential equation is given in the formula sheet. But let us do it once for all, okay? And then I want to write it here. So I want to tell you that this is not problematic at all. This is not problematic as far as I have both of them. So the only problematic one is part 2. Then method of undetermined coefficients is a little bit systematic way. I would say a little bit because it's a mixture of guesswork and analytic work to find this YP. Okay? So let us do this one first. If I give you that differential equation, you have it in the formula sheet. The general solution of this differential equation can be obtained easily by multiplying it by this integrating factor. So this becomes e to the power of ax y prime plus a e to the power of ax y is equal to 0. And the left-hand side becomes what? E to the power of ax times y prime. And the right-hand side is 0. So e to the power of ax y is a function whose derivative is 0. So it's a constant function. So then it means that y is equal to c divided by that. And this is in the formula sheet. Okay, so let me write this. So you really don't need to do it. It's always
This also.
this a is this minus a is the negative of this a.
Also, just shouldn't we, if we want to be like strict, shouldn't the y in step 1 have a different name from the y in our, like in y prime plus?
No, because the
dy?
differential equation, exactly like equations that you can use the same letter x to write different equations, but
Yeah,
when
I
you
guess.
solve them, the answers might be different. So I am saying
Yeah.
that I am writing this differential equation with the same letter y,
Mhm.
but I am calling its general solution y sub h.
Okay, but that is a separate y than the y present in step 2.
That's this one.
Yeah.
This
Yeah.
y is also with y sub p, and this y is the general solution. If you want, I can write an index for it. C.
Yeah, but
For having emphasize. Yeah.
okay, yeah.
Yeah.
But that y is not compatible with the equation in step 1, right?
No, this
That's
y.
that's not a solution to.
No, that's not the solution of that.
Yeah.
Yes. But this is not very common because if I ask you to solve this differential equation, I put this h to be able to talk about that. But if I ask you to solve this one, you just write y. And then if you want, you call it yh to use the algorithm. Yes. Anyway, this is given to you. So you see, this was not part of the algorithm, but this differential equation is so simple that we can do it once for all and use it if I need it. Yes? So the general solution is already found, so the problematic one is finding a particular solution y sub p. Okay. So the rest of the lesson today will be dedicated to understand the second part of the algorithm a little bit better. Okay. Because it is a guesswork, I cannot talk about all possible functions that you have in mathematics for the right-hand side. Yes. So there are 3 categories of important functions that we can find a method, systematic method to guess this particular solution. Yes. So f of x for these 3 cases, one of them is polynomial. One of them is a combination. So let me write an exponential function. Yes, and then a combination of sine x or any other angle, sine and cosine. Yes. So if f of x is one of these forms, then it is not probably that hard to systematically guess yp, not just random guess. Okay, let us start with a very simple one. So I would write this differential equation here for you, y prime plus y. Instead of putting x, let me put x squared. Yes? Okay, if I give you this in the exam and I ask you to solve it, so I think you understand that method of integrating factor will not work that easily for you, because then you have to guess what is a primitive function for x squared e to the power of ax. It's not that easy. But what you need to do, you decide to use method of undetermined coefficients, and you are happy about it because the right-hand side is one of these forms. It's a polynomial. So in principle, this method of undetermined coefficients that I will explain will work. What you do, you write the homogeneous one, and you take the formula sheet, you know what is y sub h. What is that? According to this general formula, is a c e to the power of minus ax. But a is 1 in this problem, so it becomes simply that. But then I want to go, this is the first part of the algorithm. For the second part, I want to guess a function whose derivative plus itself is x squared. It is not that easy to guess, but if we are wise enough, we can understand which type of functions I have to look for. Because there are infinitely many functions in the world of mathematics. I cannot just test all of them. But is it reasonable to look among logarithmic functions here for a particular solution? So it is stupid, you know. Because, for example, let us say y is ln of x. Its derivative is 1 over x. And if I add them, it becomes again a logarithmic function. Okay? I am not trying to find the best guess. There is no best guess here. One guess which works is enough. That's important. This is the logic you have to have in the back of your head. I want to find one function that works. There is no good reason to look for that one among logarithmic functions. Is it good to look among trigonometric functions? No, if y is a trigonometric function, in general, its derivative is also trigonometric, and when I add it to the function, it remains trigonometric, and it will not be polynomial. So if you want to look in your boxes of functions for a good suitable choice for this, which type of function has a likelihood, a higher chance to be a solution, what type of solution you will look for? Polynomial. Yes? At least I am not saying that might be miraculously there are other functions which work, I don't know, but at least it is not reasonable to start working with them. But when you say polynomial functions, how many polynomial functions are there? Infinitely many. But so that we have to narrow it down. Is it useful to look at for polynomials of degree 1000 there? No. Because if I have a polynomial of degree 1000, its derivative will be of degree 999. But what I want on the right-hand side is a degree 2 polynomial. So which type of polynomials you are looking for? Second degree or lower. Third degree is also not useful. You know why? Because if you start with a third degree, I agree with you, the derivative becomes second degree. But the second degree plus a third degree becomes again a third degree. But I see in front of me is a second degree. it doesn't hurt you if you go to third degree. It will work, but you are making life harder for yourself. And I told you, the logic back of your head is that I need one. I don't care the best one. There is no best one here. I just want to find one that works. Okay, but the problem is that if I ask you, okay, can you give me a second degree polynomial which satisfies this equation? This part I want you to do it analytically, not guess. So that's a mixture of guess and analytic work. The guess part of it is it's a polynomial function. That's the guess part. But the systematic way is this. I would say number 2, y sub p, I realized that a second degree polynomial has a big chance to be a solution. But how many second degree polynomials I have? Again, infinitely many. I write the most general one. And if you don't mind, let me write alpha, beta, and gamma, not to confuse this A with that A. Yes? This is the guesswork, I know, because we guessed that might be the solution is a second degree polynomial. But still, there is some analytic work to do. I am no longer guessing alpha, beta, and gamma. I am supposed to calculate them systematically. Okay? And these coefficients are undetermined. The method of undetermined coefficients. So these coefficients are undetermined yet. Okay, so what should I do? If this is going to be a solution, it should satisfy my equation. So I need yp prime here, which gives me 2 alpha x plus beta. Yes? And then I take these with me and put them back into my equation and adjusting these undetermined coefficients so that the left-hand side matches with the right-hand side. Okay, that's very simple now. I will put it back here. So this becomes 2 alpha x plus beta plus, and I have y, which is this expression. Yes? And this is supposed to be x squared. Okay? And then I arrange it a little bit, so I would write it as alpha x squared. Between these two, I have 2 x's, so I factor an x out to write it in a standard form. And then I have beta, a constant, another constant gamma there, so it becomes beta plus gamma is equal to x squared. You see, your duty is to fine-tune one single set of values for alpha, beta, and gamma so that the left-hand side matches with the right-hand side. Yes? So then what happens? I have a system. Alpha is the coefficient of x squared, but the coefficient of x squared here is 1. So alpha has to be 1. The coefficient of x here is 2 alpha plus beta, but the coefficient of x here is 0, so this should be 0. And the constant number here is beta plus gamma. Is there any constant number here? No, so it should be 0. You see, I want you to understand this is not just pure guessing, because now I can do analytic work to find them. Alpha is already found. I put it here. Beta is minus 2 alpha. Alpha is 1, so beta is minus 2. Gamma plus beta is 0, so gamma is minus beta, so it is 2. And then it means that yp is what? Alpha, which is 1, x squared, beta, which is minus 2x, plus gamma, which is 2. And I hope that you agree, it was not that simple to guess this function. So it's a mixture of guess and analytic work. The guess part is we guessed that one reasonable solution is a second degree polynomial. But there are still infinitely many of those. We didn't guess the rest of it. We calculated what it should be. So it was successful. And then what is my final step? My final step is the general solution of my differential equation. I will take this one and add it to what I got there. Yes? So it becomes c e to power minus x plus x squared minus 2x plus 2. And that's your answer. Yes? Okay, so I hope that you understand what's going on. And the reason, for example, you see why these are the only ones. And of course, I can give you harder questions. We can still combine a lot of them. Okay, but it should be among these type of functions. Can you see why? Why, for example, having a logarithmic function here does not fall into this category of undetermined coefficients? I want you to feel why these are the only famous functions available that are probably, yes?
Yes, because like the derivative of a polynomial is a polynomial, so we can.
Yeah, the category of the function will not change. So what is involved here? The function itself and its derivative. If what the right-hand side is totally different from the left-hand side, it would be a very wild guess. How can I guess? But if I have a polynomial, y is a polynomial type, its derivative is still a polynomial, and the sum of them is still a polynomial. Okay? If f of x is an exponential function, y is an exponential, the derivative of an exponential is still an exponential, so the combination of them is still an exponential function. If I have sine and cosine, what happens? The derivative of sine becomes cosine, the derivative of cosine becomes minus sine. So they go, so one of them changes to the other one at most. So if I have a combination of sine and cosine on the left, the derivative is also a combination of sine and cosine, and I still have a chance, probably, to get a combination of sine and cosine right there. But if I change it to tangent, it's useless. If I give you a tangent function here, then you have to come up with a guess, which is not easy to at all, to guess a function whose derivative plus a constant multiple of the function becomes tangent function. We cannot have guess for that. So this is why the method that I described for you in the beginning, which was not in the book, and I want you to learn it, yes, that method is a general method, but the weakness there is that calculating that integral of a product is not always easy. Yes? So, for the cases that my function has these type of forms, then method of undetermined coefficients is extremely useful, which will be a mixture of guesswork and analytic work. Any questions? So let me solve another one for you. Let us keep for the time being a polynomial again. So let me write y prime minus 3y is equal to, let me write 3 x cubed minus 2x plus 1. We want to solve this differential equation. Okay, the first step is extremely simple. The first step, you write the homogeneous one, and then you have it in the formula sheet. So y sub h is e to the power of minus a, which is 3x here. That's it. Okay, now I want to ask for your opinion. So what type of function do you think it's a good guess for y sub p? A polynomial. Of which degree?
4.
No, degree 4 works. But as I told you, degree 4 is not useful that much, because degree 4, the derivative becomes degree 3, but y is still degree 4. Then it means the left side will be a degree 4. It will work because the coefficient, you put it 0 at the end. You will be forced to put it 0. But why should I do that? So I start with a degree 3 polynomial. And of course, a degree 3 polynomial is my guess, but the rest of it I will not guess. I will write, for example, alpha. So in this problem, so you are not confused, let me write the standard one, ABC. So ax cubed plus bx squared plus cx plus d. This is the most general third degree polynomial. What I need its derivative. So it's 3ax squared plus 2bx plus c. Yes? And then what I do, I put it back into my equation. So it becomes 3ax squared plus 2bx plus c minus 3 times y. This y. ax cubed plus bx squared plus cx plus d And the right hand side, I copy and paste that one. So 3x cubed minus 2x plus 1. And then I arrange it. Okay, so let me just be patient and do it. You can do this part in your head, some parts of it. So it's minus 3ax cubed, and then minus 3bx squared, minus 3cx minus 3d is supposed to be equal to 3x cubed minus 2x plus 1. And then I have to arrange that. So minus 3ax cubed is alone. With the highest degree, I put it on the left. You see, between these two, I can factor x squared out. I can also factor a 3 out. So it becomes 3a minus bx squared. And then you see that I have this one. So let me write it here. This one and that one. I factor an x out. Yes. And then I have 3c minus 3d. Yeah, please check my calculations if you are happy with what I have done. Yes. So I put this back, I multiplied, and then I am arranging it from the highest power of x to the lowest power. And now I want to compare the left hand side with the right hand side. You know, because there are some exceptions. I will talk about that later. I hope that I'm not so unlucky that accidentally I got that special case. Okay, so, and then what should I do? I would set up a system. The coefficient of x cubed is minus 3a on the left. The coefficient is 3 here. The coefficient of x squared on the left is 3 times a minus b. The coefficient of x squared on the right is 0. The coefficient of x on the left is 2b minus 3c. The coefficient of the x here is minus 2. And finally, the constant term is c minus 3d. The constant term here is 1. So I have to solve this system. It is lengthy, but it is not guesswork anymore. Yes? So a becomes what? Minus 1. From here, a and b should be the same. If a is minus 1, b is also minus 1. And then if b is minus 1, c is 0. If c is 0, d is negative 1 over 3. It was not easy to come up with these numbers out of the blue, you know. So we are doing something really here. The guess part was this part. It was a educated guess. But then the rest of it is really analytic work. Okay, so then what is y sub p then? Y sub p is a. I have to replace a, b, c, and d here to find y sub p. So it is minus x cubed minus x squared. C is gone, minus a third. You can check if you want to make sure you go to scratch work and really check that there is no mistake you have done there by putting it back to see it works. Let us do that once. If I differentiate this, it becomes minus 3x cubed minus 2x. And let us put it back here. Yes? So y prime is minus 3x cubed minus 2x, because otherwise I will be in trouble. Minus 3 times this, which becomes plus 3x cubed plus 3x squared plus 1. Is it right? This one and that one are gone. 3x squared minus 2x plus 1. Yes. That is correct. So you don't need to check. If you are confident about your calculation so far, definitely it works. But I just double check that this is really working.
Wait, Baba.
Yes?
Did you get 3x squared minus 2x plus 1?
I differentiate. derivative of this function
Okay.
is this function.
All right.
Yes? And then I put it back into that equation, and then the rest of the calculation. Finally, the last part, which I'm looking for, is YH plus YP. YH is, where is it? It's up there. C e to the power of 3x plus this expression. And that is the answer that I was looking for. And I hope that you agree it's a good way. I mean, it's not the most general one. It only works for polynomial, exponential, and combination of sine, cosine. But if it works, it's a good method. Yes?
What is the thing with adding YH? Why do we do that?
No, I don't want to go back again. I convince you that this algorithm works by proving it.
But like,
Because if you don't do that, this is not the answer of your function. This is still one answer, but that's not the general solution.
yeah, but,
I agree that this is one possible solution for your differential equation, but it is not all of them. I want to find all of them.
but so every additive constant that would or isn't that form the C E?
No. That's only this one.
Okay.
If I add another constant, that constant should be definitely 0.
Yeah.
Nothing else. Because if you add a constant, you will not affect the derivative part, but you will immediately affect the y part. So you are not allowed. There is no freedom anymore here.
Okay.
The only freedom is to choose whatever you want for C.
Yeah.
But you cannot say that I choose one here, and that's the whole point of the general solution.
Yeah.
You cannot have more than one free parameter, because the degree of the equation is 1. Is that right? Okay. So, but let me, of course, today I will not talk about these. This is not a very hard one. But let me also practice this by solving an initial value problem. Okay. Because I have seen some of the students make some mistakes here. So I will change this differential equation. Let us make it a little bit simpler this time. So I would write, for example, y prime plus 2. Let me write square root of 2y is equal to 2x minus 1. And I will not say solve the differential equation. I will ask you to solve the following initial value problem. Okay. So the question is this: solve the following initial value problem. Do you remember what was the initial value problem? It was a differential equation to get together with an extra condition to fine-tune the constant parameter at the end. The reason I brought this up because some students make a mistake and then use this immediately there. I want you to understand that is not the case, yes? So let us solve the problem. And this would be the last problem for today. So, what do you do? The first step is to solve this differential equation with 0 on the right hand side. But this is from the formula sheet. So what is y? I will call it y sub h. It is a constant e to power minus the square root of 2x. Yes? My whole point of bringing this example is that, I don't know, for some reason students immediately put this there and find c. This is not correct, because this is the solution of this differential equation. This one is not a solution of this differential equation yet. So you are not allowed to put this initial condition immediately here and find c. You have to be patient and solve the problem in its full generality. And when you found the solution of this differential equation, use that answer to fine-tune your c. They are not the same. So that is, I want to make sure. That's it. The rest of the story is the same. So what do you guess for yp here? What is your educated guess? A polynomial of degree 1. Yes? So I would write it as ax plus b. And then I differentiate it. It becomes a put them back in my original differential equation. So it becomes a plus square root of 2 times y. What is y? Is ax plus b. And then it should be equal to 2x minus 1. And then I arrange this, square root of 2 times a times x plus a plus square root of 2b is equal to 2x minus 1. And then I set up a system, square root of 2a is 2, a plus square root of 2b is minus 1. Agree? Yes? And then from here, a becomes square root of 2 again. And I put it here. So it becomes square root of 2 plus the square root of 2b is equal to minus 1. So I want to isolate b. So this b becomes minus 1 minus the square root of 2 divided by square root of 2. Okay, so yp at the end is what? Yp is a times x plus b. b, if you don't mind, let me take a minus sign out. Yeah. This is your yp. And then what do? You write the solution is yc, yh plus yp. Okay, but now you're allowed to use the initial condition. The initial condition tells you that if you replace x with 0, the output is supposed to be 7. So I'll put 0 for x, the output should be 7. So c becomes equal to, 7 becomes equal to c, because if I put 0, it becomes 1. This will vanish. Then this becomes a little bit a strange number, but don't worry about that. So c becomes what? 7 plus square root of 2 plus 1 over square root of 2. If I take the common denominator, it becomes 8 square root of 2 plus 1 over square root of 2. And what you need to write as the answer for this initial value problem is y equals to, you have to write this strange factor here, a strange constant, and then multiply it by e to the power of minus 2 square root of 2x, and then plus square root of 2x minus the square root of 2 plus 1 over square root of 2. So that will be the solution to this initial value problem. I just randomly wrote I don't know why I put the square root of 2, makes no trouble, but anyway. The only point is that this is a common mistake. I don't know, for some reason people immediately use this to find that c. That is not correct. If you do that, you get c is 7. c is far away from 7. c is this weird constant. So if someone asks you what you got here, you will tell me this is the solution that not only satisfies the differential equation, but also this condition. Okay, and it is shown in theory of differential equations that if you have a linear equation, by the way, I need to talk about linear equations later, next time. And then it has been shown that this solution is unique. So if you have a first degree equation, first order differential equation, sorry, with some initial condition, there is one and one answer for it. Of course, there should be some conditions on this function. Let us say the function is continuous on the interval that we are working. Okay, any questions? Yeah, I think it's a good point to stop here. Thank you.